In this lesson, we're going to learn how to solve systems of linear equations using the matrix method. A matrix is a rectangular array of real numbers. The plural of matrix is matrices. So here we have 5 examples of some matrices. The dimensions of a matrix is m by n, where m represents the number of rows and n represents the number of columns. So if we're given a matrix and we're asked to state the dimensions, we want to count the rows and count the columns. So I'm going to start with this example down here at the end. Notice that we have 1, 2, 3 rows, but we only have 1 column. So the dimension of this matrix is 3 by 1. For this example, notice that we have 1, 2, 3 rows, but 2 columns. So the dimensions are 3 by 2. Likewise, we have 2 rows, 2 columns. The dimension is 2 by 2. For this matrix, we have only 1 row, but we have 1, 2, 3, 4 columns. The dimension of this matrix is 1 row, 1 column, so it's 1 by 1. Something else we need to know about a matrix is about the entry or the element or a number that's in a particular position. So the number or the entry or the element that's in the ith row and the jth column of a matrix is denoted by the double subscript notation A subscript ij. So for example, up here in this matrix, let's say we're asked to identify A subscript 1, 2. So that just means find the number A that's in the first row, second column. So the number that's in the first row, second column would be 0. Let's do a couple more. So what's A subscript 3, 1? Third row, first column, that element or entry is -7. Using the same matrix, let's find this element, A subscript 3, 3. Third row, third column. Well, the third row is down here, but I don't have a third column, so we just say that does not exist. All right, some more background about matrices. A matrix is derived from a system of linear equations as long as those linear equations are written in standard form, and that just means the constant term is on the right-hand side of the equals. This is called the augmented matrix of the system. Additionally, the matrix derived from the coefficients of the system, not the constant terms, is called the coefficient matrix of the system. We're really going to be focusing our attention only on finding an augmented matrix. All right, let's look at example 1 and 2. We're asked to write the augmented matrix for the system of linear equations and then also state the dimensions of that augmented matrix. So you have to kind of memorize when they say find an augmented matrix and the presentation is a system of equations, is that we want to create an array of numbers called a matrix. So what I do is I just look at the top equation. I look at the coefficients, 2, 1, and the constant 5. And I record those coefficients, 2 and 1, and then the constant as well. Remember, a coefficient matrix would not include the 5. All right, continuing with this augmented matrix, for the second row, I'm going to have 3, -2, and 4. And we line them up, 3, -2, and 4. Sometimes you'll see maybe a vertical bar here, maybe a stack of some dots here. And that just tells us that these are the constants and these are the coefficients of some variables. All right, see if you can do example 2, writing the augmented matrix. I see I have x, y, and z, but in the second equation down here, I don't have an x term, so I'll fill in a 0 for that. And again, if we wanted to put a vertical bar or a stack of a bunch of dots here, that would distinguish that these are the constants, whereas these numbers to the left of this vertical bar all represents coefficients of the variables x, y, and z. Let's go and do the opposite now. Given these augmented matrices, let's write a system of linear equations for them. Sometimes we just put a single brace over here to the left. It's not necessary. All right, these stack of dots right here represent that these are the constants, okay? That you can think of these dots as the equal sign. So I'm counting to the left of these dots right here, I'm counting 2 numbers. So that tells me that I have a system with probably the variables x and y. So I'll attach 3 to the x and 4 to the y. I'll put an equals and a 0. And then likewise for the bottom row. All right, so let's go ahead and do the same here. Notice that I have 3 numbers to the left of the stack of dots here. So with 3 numbers here, that indicates that I'm going to have an x, y, and z. So because the zeros here, I don't have an x term, I have a y term. I might leave a little gap here so that as I line up, I'll have something, a space here to line up the x terms. So 12y plus 3z equals 0. For the second row, notice that we don't have a z term, so I just have x and y. And third row, 1x, 7y, minus 8z equals 43. Okay, our objective in this lesson is to solve a system of linear equations using matrices, but before we can even get to that technique, we've got a lot of little parts that we have to look at first before we can put it all together and solve a system of linear equations using this technique. All right, something else that we need to be aware of is elementary row operations for matrices. That means given an augmented matrix, what are some of the things that we can do with these numbers to help us solve a system? Well, just like when we solve a system with elimination method, we can multiply rows by a number, we can add the rows down, we can do various things when solving a system by using the elimination method. And the matrix method just helps us kind of remove the letters, just keep the numbers so that all we have to focus on are these numbers right here to help us solve the system. All right, so 3 operations on an augmented matrix of a given system of linear equations producing a new augmented matrix corresponding to a new but equivalent system of linear equations. 2 matrices are row equivalent when one can be obtained from the other by a sequence of elementary row operations. That's a lot of language in there. So let's just get down to what are we allowed to do with rows of augmented matrices. Well, one thing we can do is we can actually interchange 2 rows. So if I can take row 2 and make it row 1 and vice versa. Just like taking a system of equations and moving the equations around. Something else I can do is I can multiply one of the rows by a non-zero constant. So if I wanted to multiply row 2 by 5, I'm allowed to do that. If I wanted to divide row 2 by 5, I'm allowed to do that. I just can't add or subtract numbers to a row. So I can multiply or divide a row by the same non-zero constant. The third thing that we can do is we can add a multiple of one of the rows of the matrix to another row. And just kind of think back to elimination method. Sometimes I had to multiply a row by a certain number so that I can then add and cancel, eliminate one of the terms. And that's the same thing right here. All right, it says study page 646, example 3. Then fill in the blank using an elementary row operation to form a row equivalent matrix. So what we're saying is if we start with this matrix right here, what can I do to go from this matrix to this matrix so that they're equivalent? Well, to go from here to here, I first look to see what stays the same, and I see the top row didn't change. The only thing that's changing are the numbers or the elements in the second row. The 3 goes to a 0, the 5 goes to a -4, and based on that pattern, what number would the 12 go to that's going to fit in this blank? So here's where we have to kind of put on our thinking cap and go, okay, how can I go from 3 right here to a 0 right here? What can I do within this matrix to replace that 3 and make it a 0? Well, if I divided the bottom row by 3, I'm going to get 1. And I don't want a 1, I want a 0. I can't subtract a 3 from this 3 because that's not allowed, only multiplication and division. I certainly don't want to interchange these two rows because I want the 1, 2, 3 row to be on top here. So it looks like up here, number 3 is really our only option for taking this 3 and making it a 0. So it says add a multiple of one row to another row. So let's just think about this. If I worked on the top row, and I'll look at these numbers later, but I'm just first inspecting this 1 right here. If I were to multiply this 1 by -3, I would get -3, but then I would want to add it to this 3 right here, and that would result in the 0 that's right here. Well, before I make that move, I want to double check that if I multiplied by -3 into this 3 and got -9 and added that to 5, would I get the number that's present here, a -4? And I do. So I want this 5 to go to a -4. So if I multiply -3 into 3, that gives us -9. And if I add it to 5 and replace that 5, I would get -4. So I think that's the elementary row operation that's going to be necessary to change this, this 12, to whatever number goes on this blank. All right, so let's just kind of go through this again. -3 times 1 is -3. Add it to 3, I get 0. So I'm going to write down here on this row that's changing, I'm going to say I'm going to multiply row 1 of the original matrix by -3, but then I'm going to add that number to what's in row 2, and that does result in this 0. And again, one last check. -3 times 3 is -9, plus 5 does give me -4. So I feel confident that if I multiply -3 times 2 and get -6 and add it to 12, that would give me 6, which is what should go here. So I think I found the pattern that changed the 3 to a 0 and a 5 to a -4 that's going to change the 12 to a 6. And notice how I recorded my steps right here in front of the row that changes. So the row that changed is row 2. So row 2 should be last in this little expression right here. All right, let's practice some more. Identify the elementary row operation performed to obtain the new row equivalent matrix. So this is the original matrix, and this is the changed matrix. And we have to identify what change took place. Well, notice that row 2, notice first what stays the same. Row 2 is the same from here to here. The only thing that changed was row 1. The -4 became a 1, the 8 became a -2, and the -20 became a 5. How can I make, so I always start with, how can I make the -4 into a 1? Notice it's not a 0 here, which is good, because it should be easier. Well, I don't want to interchange rows, but can I just simply take this row right here and divide it or multiply it by something that's going to give me all the new elements here? Well, -4 divided by -4 gives me 1. Does 8 divided by -4 give me -2? Yep. Does -20 divided by 4, -4, give me +5? Yep, it does. So how do I identify that? Well, I'm coming over here, and in front of this row that changed, I'm going to say in the original matrix, I'm taking row 1 of the original matrix, and I'm dividing by -4. Or another way to say that is, it's -1/4 times row 1. So dividing by -4 is the same thing as multiplying by -1/4. So we just identified the change that needed to take place to go from this top row to this row. All right, let's look at example 2. Well, I see that row 1 and row 2 are identical to the rows in the original matrix, so the only change is going to be in row 3. Somehow I need to make this 5 a 0. This 4 needs to go to a -6. -7 has to change to an 8, and 6 has to change to a -4. I'm first going to focus my attention on how do I get this 5 to be a 0. So for me right now, I'm going to cover this up and I'm going to go, how can I make this 5 a 0? I can either use row 1 or row 2 to help me. So because I have a 0, this is probably going to involve multiplying one of the rows by a number and then taking that product and adding it to this 5 to get it to be a 0. I'm going to work with row 1. If I were, I'm just going to focus my attention right here on this -1. If I multiplied -1 by 5, that would give me -5. If I added -5 to row 3, that would give me a 0. And that's great, but I've got to test that that same little pattern is going to work to change this 4 to a -6. So let's try the 5 times -2 is -10. Add -10 to 4 and replace that 4 with that new sum. So -10 plus 4 is -6. Yep, that's what I needed. All right, let's continue inspecting this third change. I need this -7 to be an 8. So keep that in the back of your brain, an 8. 5 times 3 is 15. 15 plus -7 is 8. I would change that -7 to 8. And yes, it is correct. Last inspection, 5 times -2 is -10 plus 6. Wipe that 6 out, replace it with -4, and that does confirm over here. So how do I go from this matrix to this matrix when the third row is the row that changed? Well, I took 5, I multiplied it by row 1, but then I added it to the number that was in row 3. So the row that changes should be the row that has this recording of what we did, and the row that changes should match the last term that we have right here. So this is row 3 because we changed row 3. I wouldn't have 3 up front here. All right, we have some more examples here. It says fill in the blank using elementary row operations to form an equivalent row, a row equivalent matrix. So we're going from this matrix to this matrix. Top row doesn't change. Bottom row changes. First thing I inspect is to go from a 2 to a 0. That probably means I'm going to multiply the top row by something, add it to the bottom row, and replace that number in that position. To go from a 2 to a 0, I would multiply the top row by -2 and add it to the bottom row. So -2 plus 2 gives 0. Let me see if that prediction works with this last number changing a 5 to a -1. So -2 times 3 is -6 plus 5 is -1. So I'm going to multiply row 1 by -2 and add it to row 2. Notice that this expression is right out in front of row 2. So -8 plus 10 is 2. All right, let's look at example 4. And actually, we have a couple of changes here. So if you want to attempt this on your own, I would just encourage you to turn off the video, attempt it, and then come back and check your work. Row 1 stays the same all throughout. So I'm going to focus on row 2. How do I go from a 3 to a 0? Well, I'm going to try and take advantage of this 1. I think if I multiplied row 1 by -3 and added it to row 2, I would get the 0 here. Well, let's see if that's the same thing that's going to take place to change an 8 to a 5. -3 times 1 plus 8 does give 5. So right out in front here, I'm going, okay, -3 times row 1 plus what's already in row 2 over here gets replaced in these blanks. So -3 is -12 plus 10 is -2. -3 times -1 is +3 plus 3 is 6. Okay, so let me drop down here. So for this row right here, the -2 became a 0. Well, how am I going to take -2 and make this a 0? I'm going to go back up here to row 1. This 3 right here is going to be too hard to work with. I like to work with 1s when multiplying. If I were to multiply row 1 by 2 and add it to -2, I would get 0. Let's check the next one. Row 1 by 2 is 2. 2 plus 1 is 3. So I feel pretty good that I'm going to multiply row 1 by 2 and add it to row 3. This is row 3. It matches what's in front. It's in front of row 3. This last term is row 2. It's in front of the second row. All right, let's complete these blanks right here. So twice row 1 is 8. 8 plus 12 is 20. Twice row 1 is -2 plus 6 is 4. So I'll put a 4 here. Okay, now from this matrix to this matrix, top row doesn't change. The bottom or the middle row changes. Let me inspect the last row, has a 0, 3, so does this one. So I think they want me just to bring over the 20 and the 4. Okay, so now I'm going to compare this row 2 to this row 2. The 0s stayed. The only thing that changed was the 5 was made into a 1. Well, since 5 was made into a 1 and not a 0, I think I can just take this second row and divide this 5 by 5, and I would get 1. Likewise, 0 divided by 5 is still 0, so that 0 wouldn't change. So I think that's going to be the row operation. I'm going to divide by 5. So I'm going to take what's in row 2 and divide by 5. And again, that's the same thing as saying 1/5 times row 2. So 0 divided by 5 is 0. 5 divided by 5 is 1. -2 divided by 5 is a fraction. 6 divided by 5 is a fraction. I won't worry about changing those. It doesn't matter. I'm done. I don't have to make any more changes, so those fractions are just fine. All right, so far we've looked at a matrix, we've looked at the dimensions, we've looked at certain elements and certain positions, we've looked at row operations. Okay, all of this is going to help us in solving a system of linear equations using the matrix method. All right, we still have some more background before we can put it all together. I recommend pausing the video, reading through this language, reading about what it means to be in row echelon form and what it means for a matrix to be in reduced row echelon form. A matrix in row echelon form has the following properties. Any rows that consist entirely of zeros occur at the bottom of the matrix. For each row that does not consist entirely of zeros to be in row echelon form, the first non-zero entry is a 1, not a 5, not a 7. It's called a leading 1. For two successive non-zero rows, the leading 1 in the higher row is farther to the left than the leading 1 in the lower row. All right, now it goes on and says, okay, that's all row echelon. What about reduced row echelon? So a matrix that's already in row echelon form is in reduced row echelon form when every column that has a leading 1 has zeros in every position above and below its leading 1. Note here, the row echelon form of a matrix is not unique. The reduced row echelon form of a given matrix, however, is unique. That's not too important for what we're doing, but that was just some language I wanted to get out. All right, I'm sure if you're like me, when I first read that, I go, oh, that was a lot of information. I need to look at some examples. So actually, I have some for us. So we're going to state whether the given matrices here are in row echelon or reduced row echelon. So we have 6 of them to look at. All right, a row echelon matrix, okay, would be in that form if we had any row that consisted entirely of zeros and it was at the bottom of the matrix. So I can see in B here, example B, you can see row 2. It has all zeros in it. That row should be at the bottom of this matrix, and it's not. So this matrix is not row echelon, nor is it reduced row echelon. If a matrix is not in row echelon form, then there's no way it can be reduced row echelon. So matrix B is neither. All right, I do see this matrix D right here. It has a row of zeros and it is at the bottom of the matrix, so that's good. To be in row echelon form, it says every first non-zero entry has to be a 1. So in row 1, I see I kick off or I lead off that row with a 1. That's good. Drop down to row 2. This is a 0 entry. The first non-zero entry is this number right here, and it is a 1. Drop down to the next row. I have a 0, 0. So the first number that I get to that's not 0 should be a 1, and it is. Furthermore, this 1 has to be 1 over from the preceding row. This 1 has to be over 1 position from the preceding row. So it's like you create this stair-step pattern of 1s here. It's not always the case that it kind of goes all the way on a diagonal like that. Sometimes we might have a 0 here, but a 1 here, and that's okay. All right, so at least we know this is in row echelon form, so I'm going to go ahead and record that, row echelon. And I know you don't have this, but I'm just kind of illustrating it. Okay, now is this matrix in what we call reduced row echelon? If you go back and read that language, what it says is when you identify the ones that lead off the row, you look down below and up above that 1, and all you can have are zeros. No other numbers. So definitely below this 1, I have a bunch of zeros. So let's come over here to this one. I look above, I look below that 1. Couldn't get that word out. I have nothing but zeros. Okay, I jump over here to this one, look up above and below, nothing but zeros. Okay, and then here, well, what do I have? I have a 0, not a 1. So let's look at matrix D. Because all these numbers are not zeros, this cannot be in reduced row echelon form. I thought it was going to be, but it's not. So this is just row echelon. All right, let's go back to matrix A. You know, I almost want to say this is reduced row because this isn't a 1. This is a 0. Oh my goodness. And I don't want to redo a 30-minute video because of that. Yes. I'm going to call this reduced row echelon. I got swayed by these numbers, but that's okay because that's not a 1. All right, let's go over to A. I see 1s down the diagonal. I see a bunch of zeros, but at this one, if I look above, that's not a 0 above that 1. So this is just row echelon. So this language will be more important for us when we get to solving our matrices. Okay, so let's look at where we at. C? All right, I have a 1 that leads off this row. I have a 1 that leads off this row. It's okay that I skipped a spot here. The first non-zero entry is a 1. First non-zero entry is a 1. This is row echelon. But when I look at this 1 and I look above it, I don't have a 0. So this is just row echelon. Sometimes I see a dash here, sometimes not. All right, let's try E and F. All right, in row or matrix E, well, I don't have a 1 here, so this is neither. So let's look at F. I see 1s down the diagonals, at least here, at the first non-zero entry, all zeros above. So I would say this is in reduced row echelon. All right, so let's just double check. The matrices in A, C, and D, A, C, D, and F, A, C, D, and F are row echelon. The matrices in, I think that should be a D. The matrices in D and F are in reduced row echelon form because every column that has I cut off some of this and below it's leading 1. Right, the matrix in B is, it probably meant to say is not in row echelon form because the row of all zeros does not occur at the bottom. The matrix in E is not in row echelon form because the first non-zero entry, that probably should have said is a 2 right here. So I had to enlarge this so you guys could see them, so that's why you're not seeing those directions. All right, we've got a checkpoint here too. Determine whether the matrix is in row echelon form. If it is, determine whether it is in reduced row echelon form. All zeros, bottom row, we're good to go. Row 1 starts off with the 1. Row 2 starts off with the 1. Looks like above all these ones, we have, and below these ones, we have zeros. This doesn't matter that this is a 0 here and there's numbers above it. So we're going to say it is in reduced row echelon form. Okay, so why do we need all that information? Okay, well, that's actually going to help us solve by hand, okay, some matrices, or some systems of equations using matrices. Thank goodness we'll only have to do a couple of these, and then we can use our calculator to help us with this. All right, it says write the matrix in row echelon form. So we're done identifying if our matrix is in row echelon form. Now it's time for us to perform row operations and get this matrix to be in row echelon form. So that's going to take some time. So I'm going to start with you in another video to complete changing this matrix to row echelon form.